Welcome everyone to AI on AI, the podcast where we delve deep into the technologies shaping our future, talking directly with the minds exploring the frontiers. Today, we're tackling something truly fascinating, moving beyond the static snapshots of current AI towards models that seem to think over time. We're discussing the Continuous Thought Machine, or CTM. We've got a fantastic panel to unpack this. We have an expert in neural architectures. Welcome.
Glad to be here. It's an exciting concept.
We also have an expert specializing in temporal dynamics in AI. Thanks for joining.
Thanks for having me. Time is definitely of the essence here.
Absolutely. And bringing the crucial business perspective, our expert in AI strategy and adoption. Welcome.
Pleasure to be here. Looking forward to discussing the so what for businesses.
We also have an expert in ML performance and evaluation with us. Great to have you.
Happy to dive into the results and how this thing actually performs.
And an expert focused on AI applications and industry use cases. Welcome.
Excited to explore where this could actually be deployed.
Offering a different angle, we have an expert on future AI directions and potentially some contrarian views. Welcome.
Thanks, always good to question the assumptions.
And finally, our expert in AI interpretability and biological plausibility. Welcome to the show.
Thank you. Bridging AI and neuroscience is key here.
All right, let's set the stage. Expert in neural architectures, why the need for something like a CTM? What's the limitation with today's dominant deep learning models that this paper is trying to address?
Great question. Most current neural networks, even the huge ones, are fundamentally feed-forward or use recurrence tied strictly to input sequences. Think of them like taking a photograph, a static snapshot. Biological brains, however, are incredibly dynamic. Information isn't just processed, it evolves over time through complex neural activity, oscillations, synchronization. The timing is critical.
Exactly, standard activation functions, like RayLU, are basically abstractions of a neuron's firing rate, collapsing all that rich temporal dynamic into a single static value. It's efficient for computation, sure, but as the paper argues, and many in the field believe, we might be throwing the baby out with the bathwater, losing fundamental aspects of intelligence needed for things like common sense, fluid generalization, and true reasoning.
So we've simplified things for computational efficiency, but maybe lost some magic related to time. The paper mentions Francois Collett and Gary Marcus, who have pointed out gaps between AI and human cognition. Is this CTM trying to bridge that gap by reintroducing time?
That's the core idea. The CTM introduces time not just as something to process in sequential data, like words in a sentence, but as an internal dimension over which thought can unfold. They call these internal ticks. It's like, instead of just reacting to an input, the model has internal steps to mull it over, even for a static image.
Okay, internal ticks, like the brain taking a moment to process. What are the other key pieces? The paper highlights two more core innovations. Expert in neural architectures, can you walk us through the neuron-level models?
Right, the NLMs, this is pretty novel. Instead of every neuron using the same simple activation function, each neuron in the CTM gets its own set of weights, its own mini-model. This NLM doesn't just look at the immediate input pre-activation, but at a history of its recent inputs. So each neuron processes incoming signals over a short time window using its unique parameters.
So it's like giving each worker on an assembly line not just a standard wrench, but a specialized toolkit and a memory of the last few items they worked on.
That's a decent analogy. It allows for much richer, more complex individual neuron dynamics than just a simple on-off or graded response. You see those complex activity patterns emerge in Figure 4 of the paper, much more varied than you'd get otherwise.
Fascinating. And the third pillar, expert in temporal dynamics, the paper talks about neural synchronization as a latent representation. That sounds complex.
It is, but it's directly inspired by neuroscience. Neural synchronization, the coordinated firing of neurons in time, is believed to be crucial for cognitive functions like attention, memory, and binding information together in the brain. The CTM tries to capture this.
How does it capture synchronization?
Instead of using the neuron activations at a single point in time, Z-letter 1D461, as the main state, the CTM computes a synchronization matrix. Essentially, it measures how pairs of neurons' activity patterns correlate over the history of internal tics. Think of it like measuring the resonance or harmony between different instruments in an orchestra over the course of a musical piece.
Okay, orchestra analogy. I like it. So the relationship between neuron activities over time becomes the representation, not just the activities themselves.
Precisely, and this synchronization matrix, or rather specific pairs sampled from it, is then used directly to query input data via attention or to produce the final output, like a classification. It's a fundamental shift, using the dynamics as the code.
And they introduce a learnable decay factor, right? So some pairs can focus on recent history, others on longer-term patterns.
Yes, the letter 1D45F, letter 1D456, letter 1D457 parameter. It allows the model to learn how much temporal depth matters for different pairs of neurons, adding another layer of flexibility. It's like adjusting how long the echo lasts for different parts of the orchestra.
Let's talk performance. Expert in ML performance, the paper tests this across a wide range of tasks: ImageNet, mazes, sorting, parity, Q&A, even RL. What stands out?
What stands out isn't necessarily state-of-the-art accuracy across the board. The paper is upfront that this is about introducing the concept, not breaking records yet. On ImageNet, it gets decent results, 72.47% top one, but the way it gets there is interesting.
How so?
The internal tics allow for adaptive computation. Figures 2 and 3 show it can stop thinking early for easy images where it reaches high certainty quickly, but continue processing for harder ones. This isn't forced by a special loss, it emerges naturally. It's like the 80-20 heuristic, maybe 80% of the images need only a few ticks, saving compute.
Expert in AI strategy, does this emergent adaptive compute catch your eye?
Absolutely, efficiency is a massive driver in AI adoption. The idea that a model could naturally adjust its computational spend based on task difficulty without complex add-ons like PonderNet's halting mechanism or specialized early exit layers is very appealing. It suggests potentially lower inference costs and better resource utilization, which always gets business leaders interested.
And the calibration results on ImageNet and CIFAR10 are noteworthy too, Fig3C, Fig10B. The CTM seems surprisingly well calibrated. Its confidence scores align well with its actual accuracy. That's often a struggle for modern NNs and crucial for trustworthy AI. It even seemed better calibrated than the human baseline in the CIFAR10H comparison.
Wow, better calibrated than humans. Our interpretability expert, any thoughts on why that might be? Does this internal thought process help?
It's speculative but plausible. The process of accumulating evidence or refining a representation over internal tics captured by the synchronization might lead to more robust confidence estimates compared to a single feed-forward pass. The model isn't just making a guess, it's going through a temporal process, and perhaps the stability or convergence of that process informs the certainty. The visualization of certainty increasing over tics, Fig5, supports this intuition.
Let's move to the maze task. Expert in performance, this seemed like a key test for sequential reasoning.
Definitely. They designed it to be tough, outputting the entire path as a sequence of moves, and crucially, without positional embeddings for the attention mechanism. This forces the model to build its own internal spatial map, relying purely on its dynamic state.
Like navigating a pitch-black room by touch and memory.
Exactly, and the CTM performed remarkably well, Fig7, far surpassing LSTM baselines which struggled, even with more parameters. It learned to trace the path with its attention over the internal ticks, Fig 8.
Building on Expert 4's point, this really highlights the potential power of the NLMs and synchronization. The NLMs provide the local temporal processing, and the synchronization seems capable of integrating that into a coherent, evolving state that represents the map and the agent's position on it. It has to imagine the next step based on its internal state to query the right part of the maze image.
And the generalization results are quite compelling, Fig 9. The CTM trained on 39x39 mazes could solve much longer paths and even generalize, albeit with reduced accuracy, to larger 99x99 mazes by reapplying its learned procedure. This suggests it learned a general maze-solving algorithm, not just memorized paths.
Expert in applications. Where could this kind of spatial reasoning and planning capability be useful?
Obvious areas are robotics and autonomous navigation, agents needing to build internal maps of complex, potentially partially observed environments. But also think about logistical planning, network routing, or even simulating complex processes like molecular interactions, where understanding spatial and temporal relationships is key. If it can genuinely build and query an internal world model without explicit positional cues, that's a significant step.
The paper also covers sorting parity and a Q&A task on MNIST digits. Any quick highlights there? Expert in performance.
The sorting task, Fig 15, showed the CTM using variable wait times internal ticks related to the difficulty of placing the next number, echoing Graves' work on adaptive compute. The parity task, Fig 19, 20, showed it learning sequential algorithms, sometimes even learning a reverse path strategy, suggesting planning.
Okay, let's bring in our contrarian expert. This all sounds very promising, maybe too promising. What's the catch? Or what are we potentially overlooking?
Well, let's pump the brakes slightly. First, the elephant in the room, computational cost. These internal ticks mean sequential processing. We can't parallelize the thought dimension like we can layers in a standard DNN. Training and inference will be slower. The paper acknowledges this limitation. Is the added richness worth the slowdown in a world obsessed with scaling?
That's a fair point. The sequential nature is inherent. However, the adaptive compute aspect could mitigate inference costs on average if many tasks are easy for the CTM.
Perhaps, but my bigger question is about the core mechanisms. Are NLMs and this complex synchronization truly necessary? Or are they a very elaborate way to achieve what sophisticated attention mechanisms or state space models might accomplish more directly? We saw LSTMs fail here, but maybe other modern recurrent architectures could compete if tuned appropriately for this internal thought paradigm.
That's the contrarian view I was expecting. Is the biological inspiration potentially leading us down a complex, perhaps less optimal, path compared to purely function-driven engineering? Expert in interpretability and bioplausibility, how strictly should we adhere to biology?
It's a critical question. The paper rightly states the goal is borrowing concepts, not strict biological realism. Real neurons don't have perfect access to their precise activation history like these NLMs. However, the emergent properties are interesting. The paper shows complex dynamics, Fig 4.12, and even hints at traveling wave-like phenomena, Fig 6, which are observed in brains. Synchronization itself is a core neuroscience concept.
From a business strategy perspective, the trade-off is always key. If this approach unlocks genuinely new capabilities, robust reasoning in complex dynamic systems, reliable memory over long contexts, truly adaptive compute, then the initial performance or speed gap might be acceptable for high-value applications where current tech falls short. But the path to proving that value proposition needs to be clear.
Let's talk about those applications. Expert in AI applications, assuming the tech matures, where do you see the CTM or its descendants making a real impact?
Building on earlier points, advanced robotics needing real-time world modeling and planning. Complex system simulation, think climate modeling, financial markets, or even social dynamics where temporal dependencies are intricate. Drug discovery, understanding protein folding dynamics. Anywhere that requires not just pattern recognition, but understanding evolving processes and performing multi-step reasoning based on an internal model of the situation. Consider, for instance, a supply chain optimization system. A A CTM-like model could potentially build an internal dynamic model of the entire chain. Think through various disruption scenarios using its internal ticks, and predict downstream consequences with higher fidelity than static models, leveraging that synchronization to represent the complex interdependencies over time.
That's a tangible example. Let's inject a bit of humor here. With all these internal ticks and complex dynamics, expert in neural architectures, how hard is this thing to debug? Are you basically trying to psychoanalyze the machine when it goes wrong?
It's definitely more complex than debugging a standard feed-forward net. You're not just looking at activations, but activation histories and their synchronization. It's less psychoanalysis, maybe more like being an orchestra conductor trying to figure out why the brass section is out of sync with the strings. The visualizations in the paper attention maps over time, neuron traces become crucial diagnostic tools.
I can imagine. So, looking ahead, the paper mentions future work like language modeling, training in continuous open worlds, exploring plasticity. Expert in temporal dynamics, what excites you most?
The potential of synchronization as a representation is still largely untapped. The paper subsamples pairs, using the full high-dimensional synchronization matrix, d-squared complexity, could unlock richer representations. Exploring its use for memory, as the paper suggests, is fascinating, thinking of synchronization patterns as encoding experiences rather than just states.
Expert in future AI, any final thoughts on where this kind of research leads?
I think the key takeaway is the exploration of dynamics as a computational primitive. Whether CTM's specific approach is the ultimate answer or not, it pushes us to think beyond static architectures. Maybe the future isn't just bigger transformers, but architectures that explicitly model and leverage time and internal state evolution. However, we also need to ensure we don't get lost in mimicking biology for its own sake.
A perfect note to end on. We've journeyed from the limitations of current AI through the intricate mechanisms of the continuous thought machine, its internal ticks, neuron-level models, and the fascinating concept of neural synchronization, explored its performance on diverse tasks, debated its practicality and biological ties, and peered into its future potential. My huge thanks to our panel today. Our expert in neural architectures, expert in temporal dynamics, expert in AI strategy, expert in ML performance, expert in AI applications, our expert offering future directions, and our expert in AI interpretability. A truly insightful discussion. And thank you for tuning into AI on AI. Join us next time as we continue to explore the cutting edge of artificial intelligence. This paper introduces the continuous thought machine. It integrates brain-inspired neural timing into deep learning. The model uses neuron-level processing and synchronization. Neuron-level models mean each neuron processes signal history uniquely. This creates rich, dynamic patterns of neural activity over time. Neural synchronization captures how these neuron activities align. Synchronization is used directly as the model's internal representation. The model computes along an internal timeline using steps called internal ticks. This allows thinking that is separate from input data timing. The continuous thought machine showed strong performance across diverse tasks. These included image classification, maze solving, sorting, and parity computation. Parity computation involves tracking sequences of positive and negative values. It also succeeded at question answering and reinforcement learning tasks. The model naturally performs adaptive computation. It uses more internal ticks for harder problems and fewer for easier ones. This happens without needing special training adjustments. It solved complex mazes without needing location information. This suggests it builds internal maps to navigate spaces. The model demonstrated good memory recall capabilities. It recalled information encoded only in past activity patterns. An unexpected finding was the model's high result calibration. Calibration means its confidence level accurately reflects its correctness. The researchers observed complex internal dynamics, like traveling waves. This suggests a step towards more biologically realistic artificial intelligence. Limitations include longer training times due to sequential processing. Individual neuron models also add parameters. Future work may explore language tasks and continuous learning environments. The research highlights neural timing and synchronization as powerful artificial intelligence tools.